You know, I think if you were to ask most people what the biggest threat to a modern AI data center is, they'd probably say, I don't know, a sophisticated cyber attack. Or maybe like a massive grid failure.
Right, something highly technical or malicious.
Exactly. But if you actually look closely at the engineering schematics coming out of the industry right now, you realize the most terrifying enemy these facilities face is actually a lot more, um, well, primitive. It's just heat.
Oh, absolutely. It's the physical reality of the hardware.
Yeah. Like you upload a file or you run this massive generative AI prompt, you train a neural network, and you probably imagine that workload existing in this, weightless, clean, ethereal cloud.
Which is a brilliant piece of marketing,
It really
honestly.
is. But today, we're going to pull back the curtain on that illusion for you.
Because the cloud is actually incredibly heavy. I mean, it is remarkably dense, and it is running so hot right now that traditional physics are basically forcing a complete reimagining of how the internet is physically built.
Yeah, and we have the actual blueprints for this. We've got our hands on a stack of highly technical data sheets and some really revealing user interface screenshots, actually straight from Supermicro.
Which are fascinating to look at.
They really are. We are looking at their SuperCloud Composer, which we'll just call SCC to keep it simple, and specifically their In-Row Coolant Distribution Units, or CDUs. So, okay, let's unpack this. The mission for you and us today in this deep dive is to decode exactly how these massive data centers are solving a literal thermodynamic crisis.
And we're going to do it by translating all that hardcore engineering jargon into the actual physical mechanisms that are keeping the AI revolution alive right now.
Right, because reading standard hardware specs, I mean, that really only gives you like a table of contents.
Yeah, exactly. What this source material actually represents is more of a survival guide. When you look at the trajectory of artificial intelligence and big data, these workloads are pushing legacy air cooling to its absolute physical limits.
The actual mechanism of just blowing chilled air across hot microchips is fundamentally breaking down.
It is. It just doesn't work anymore at this scale.
And I want to focus on that breakdown for a second because the source material explicitly frames this new technology as the solution to demanding AI workloads. If you've ever stood in a legacy data center, you know that sound.
Oh, the noise is unbelievable.
It's deafening. It's this constant roar of massive fans and HVAC units, which the industry calls CRA units, right? Computer room air conditioning.
Right, CRAC units.
But air is essentially an insulator, isn't it? I mean, we literally trap air between two panes of glass to keep the winter cold from getting into our living rooms.
That's a perfect way to think about it. Air has a terrible specific heat capacity. To cool a standard server with air, you have to force just an enormous volume of it across the heat sinks, pull that hot air into a return plenum, cool it down with massive compressors, and then push it back.
It's moving wind around, basically.
Exactly. But when you look at modern GPU architecture racks that used to consume maybe, I don't know, 10 or 15 kilowatts of power, they're now pushing 40, 80, or even over 100 kilowatts.
In a space that's no larger than a standard telephone booth.
Right. And the air molecules are just too far apart to absorb and carry away that density of thermal energy fast enough.
So you could engineer a literal Category 5 hurricane inside the server room, and those advanced AI chips would still, like aggressively throttle their
I
performance?
think they'd throttle, or honestly, they would just physically melt.
Wow. Which brings us to the physical reality of the solution Supermicro is deploying here. And I have to say, the numbers in these specs stop me in my tracks.
The physical footprint is daunting, yeah.
It really is. We are looking at the In-Row CDU, and it measures 850 millimeters wide, 1,300 millimeters deep, and 2,300 millimeters high.
It's massive.
So for those of you trying to visualize this in your physical space, imagine an incredibly tall, extremely deep, like industrial commercial refrigerator.
But far, far denser than any refrigerator.
Way denser. The datasheet explicitly lists the weight. When this unit is sitting completely empty, like no fluids inside at all, it weighs just under 1,000 kilograms.
And that's empty.
Right. When it is solely commissioned and filled with coolant and facility water, it pushes 1,200 kilograms. That is well over a ton of metal, pumps, and liquid.
Sitting right there on the floor.
And I have to push back on this design choice for a second because a server room is typically a very delicate environment, right? You have raised floors, you have fragile fiber optic cables running everywhere in these pristine white aisles.
This is highly controlled.
And the solution is to drop a 1,200 kilogram plumbing system directly in the middle of it.
I know, it seems counterintuitive. But you have to look at the structural history of data centers and the strategic placement detailed in the text. The source specifies that this In-Row CDU appliance is positioned specifically on the left side of a fully populated liquid-cooled rack.
Oh, on the left side specifically.
Right, and the keyword there is In-Row.
Meaning they aren't hiding this massive plumbing unit in a basement utility closet somewhere. It is sitting shoulder to shoulder with the actual server.
Exactly. This is the core paradigm shift. For decades, data centers relied on room-level cooling. You air-condition the massive warehouse, and you push the cold air under a raised floor, and you basically just hope enough of it reaches the hottest racks.
Which sounds incredibly inefficient.
It's terribly inefficient. You lose so much cooling capacity over the distance. So in-row cooling abandons the room entirely. It brings the cooling apparatus directly to the heat source.
So you are isolating the thermodynamic exchange to the exact millimeter where the heat is being generated.
Precisely.
But dropping a literal ton of weight onto a raised floor still sounds like a structural nightmare to me.
Oh, it absolutely requires architectural reinforcement. You cannot just roll a 1,200 kilogram footprint onto standard office tile.
Right, it would crash right through.
Yeah, data center floorings, those raised tiles you mentioned, they have to be specifically engineered with reinforced pedestals to handle these massive, concentrated, static loads.
Okay, but facility managers are willing to undertake that kind of structural retrofitting.
They have to be. They're willing to do it because of the sheer volume of heat this single unit can handle, which the source material actually quantifies in megawatts.
Let's dig into that energy equation because the capacity numbers here are just staggering. The data sheet highlights a 1 megawatt approach temperature, 50 degrees Celsius cooling capacity.
Which is a huge number.
Yeah, you hear the word megawatt in science fiction movies all the time, usually right before a laser explodes or something. But in a physical engineering context, a megawatt is an astronomical amount of energy to manage.
To give you a sense of scale, a single megawatt is 1 million watts.
1 million watts of heat.
Exactly. Let's step away from the abstract and look at the actual computing density this enables. If we look at the latest generation of AI hardware things, like, say, NVIDIA's H100 or B200 architectures, a single, fully populated, dense server rack might pull somewhere around 40 to 50 kilowatts of power.
Okay.
And some of the extreme designs push maybe 100 kilowatts.
So if the single CDU handles 1 million watts of heat, we aren't just talking about cooling one single server. This single appliance could absorb the thermal output of an entire row of ultra-dense, multi-million-dollar AI infrastructure all at the same time.
Yes. And if you look closely at the UI screenshots provided in the source material, there is a fascinating discrepancy that suggests the hardware is actually scaling even faster than the marketing copy.
Oh, I saw this.
Yeah. The text of the datasheet proudly claims a 1 megawatt capacity. But if you analyze the screenshot of the CDU list screen, which displays the actual product, SKUs, serial numbers, and the live capacities the software is managing, those models are clearly labeled 1.3 MW.
It's like the software engineers are already dealing with the next generation of hardware while the marketing team is still, printing the brochures for the current one.
Exactly. The pace is just relentless.
It really shows you the rapid iteration in this space. Managing 1.3 million watts of heat out of a single footprint is just mind-bending.
It is.
But here is the piece of data from the specs that I find most fascinating. We know it removes over 1 million watts of heat, but to do that job, its maximum power consumption is only 18.5 kilowatts.
What's fascinating here is that ratio. That is the entire reason liquid cooling exists. It takes just 18.5 kilowatts of electrical power to transport 1,000 kilowatts or 1 megawatt of thermal power completely out of the room.
I understand that liquid is more efficient than air, but that ratio almost feels like it violates the laws of thermodynamics. Like, how does an 18.5 kilowatt machine neutralize 1 million watts of heat?
Well, because it isn't neutralizing the heat.
Oh, right.
Heat cannot be destroyed, it can only be moved. So that 18.5 kilowatt power draw is strictly a parasitic load.
A parasitic load.
Yeah, it is only providing mechanical work. It spins the impellers and the pumps, it powers the sensors, it opens the valves, and it runs the control boards.
So you are basically just paying the toll for the transportation network. You're not fighting the heat itself.
Precisely. Once you introduce a fluid into the system, the fluid does the heavy lifting via its natural physical properties. Water is thousands of times denser than air, and it has a remarkably high specific heat capacity.
It just eagerly absorbs all that thermal energy.
It does. The electricity is just there to keep the fluid moving so it can dump that heat elsewhere. And maintaining that continuous movement is so critical that the source material specifically highlights an ATS, an automatic transfer switch, for dual power sources.
Because if the power to the cooling unit drops, even for just a few seconds, the servers don't just get warm, they cook.
In a high-density liquid-cooled rack, if the fluid stops moving while the chips are processing a heavy AI workload, the thermal mass of the silicon will exceed critical failure temperatures in a matter of seconds.
Seconds, wow.
Yeah, an ATS monitors the voltage from the primary power grid. If it detects a drop or a total failure, the switch physically clacks over to a secondary grid or an on-site generator in milliseconds. It guarantees that those 18.5 kilowatt pumps just never stop spinning.
Which brings us to the actual plumbing, because keeping those pumps spinning is really only half the battle. You have to understand what they're pumping.
With the fluids themselves.
Yeah, this CDU manages an incredibly sophisticated tale of two completely distinct liquid loops. They interface in the middle, but they serve two very, very different worlds.
The primary and secondary systems, this is where the physical engineering gets incredibly elegant, but also, highly technical.
Let's break down these two loops, starting with how they connect. The datasheet notes they meet at the heat exchanger via 4-inch ANSI 150 PAL-B flanges.
Heavy-duty stuff.
Yeah, 4-inch ASI flanges are heavy-duty bolted steel connections. You see these in chemical plants and oil refineries. That is serious industrial hardware for a building that's filled with sensitive microchips.
They use hardware of that grade because of the sheer kinetic energy of the fluid moving through the system. Let's look at the parameters of the primary side, which the text refers to as the facility side.
Okay.
This is the water coming from the massive cooling towers on the roof of the data center, or maybe even from municipal water lines.
Right, like the raw street water.
Exactly. The specs say the supply temperatures here follow ASHRA W45 standards, ranging anywhere from as low as 2 degrees Celsius up to 45 degrees Celsius.
That's a huge range.
It is. The flow rate is a massive 1,200 liters per minute. The maximum pressure is 1 megapascal, and it requires filtration of less than 300 micrometers.
Okay, there's a lot to unpack there. First, let's translate 1 megapascal for a second. That is roughly 145 psi, or pounds per square inch.
Which is high.
Very high. For context, the tires on your car are probably inflated to about 35 psi. So the primary loop is pushing an immense volume of water, about 317 gallons a minute, at 4 times the pressure of a car tire.
Inside a server room.
Right. And the water itself is relatively rough. A 300 micrometer filter will catch rust flakes, sand, or large debris coming from the city pipes, but it allows microscopic elements to just pass right through.
Right, it's not perfectly pure.
Now, contrast that violently high-pressure, somewhat gritty primary loop with the secondary side, which the source calls the IT side.
This is the side that matters most to the hardware.
Yeah, this is a fluid that actually leaves the CDU, travels into the server racks, and snakes its way through the delicate manifolds that sit directly on top of the GPUs.
And this environment is strictly controlled.
Completely different rules apply here. First, it doesn't use massive volumes of water. The system holds exactly 100 liters of a very specific fluid, propylene glycol, at a 25% weight concentration.
Not just water.
Right. And the pressure is aggressively capped at 0.5 megapascals, which is about half the pressure of the primary side. The filtration requirement is an incredibly fine 50 micrometers. And perhaps most importantly, it relies on 2 and redundant pumps.
So we basically have two distinct worlds here. We have the rough, high-pressure, high-volume facility water on one side, and we have the tightly controlled, lower-pressure, hyper-filtered, chemically treated secondary fluid on the other.
Okay, I want to try an analogy to explain how these two systems interact without ever actually touching, because the heat exchanger is kind of the unsung hero here.
Oh, I'd love to hear this.
Imagine a high-rise building with 2 massive highways stacked perfectly on top of one another, but they are separated by a glass ceiling.
Okay, I like this visual. Walk me through it.
So the lower highway is our primary loop. It's chaotic. You've got huge diesel trucks, different temperatures, moving super fast at high pressure. That's our facility water.
Right.
The upper highway is our secondary loop. It's the VIP lane. It only allows specialized, highly tuned sports cars, our propylene glycol. The vehicles on the lower highway and the upper highway never ever mix. The glass barrier is completely sealed.
Right, no crossover.
But if the sports cars on the top highway are burning hot from running laps around the AI servers, They compress their tires against that glass floor. The heat from the top highway radiates directly through the glass and gets absorbed by the massive, cold trucks rushing by on the bottom highway, carrying the heat out of the city.
That perfectly captures the mechanism of a plate heat exchanger. It really does. In the actual CDU, that glass floor is essentially hundreds of incredibly thin corrugated titanium or stainless steel plates stacked together.
Oh, no.
So the hot glycol from the servers flows over one side of a plate, and the cold facility water flows over the opposite side. The fluids never mix, but the thermal energy conducts rapidly through the micrometer-thin metal. It's a brilliant physical transfer of energy.
It is brilliant. But you brought up the glycol, and this is something you might be wondering as you listen to this. Why go through the trouble and expense of using a 25% propylene glycol mix in that secondary VIP loop?
It's a great question.
Why not just use heavily filtered purified water? Water is cheaper, and pure water is actually a slightly better thermal conductor than a glycol mix, isn't it?
Pure water is a slightly better conductor, yes. But pumping pure water through the microscopic cooling channels inside millions of dollars of computing equipment introduces 3 catastrophic liabilities.
Ooh, catastrophic liabilities. Let's hear them.
First, freezing points. You noted that the primary facility water can enter the building at 2 degrees Celsius, which is barely above freezing.
Right.
If your secondary loop is running pure water and the AI servers suddenly drop their workload, meaning they stop generating heat, that 2-degree facility water can cause localized freezing inside the heat exchanger.
Oh, wow.
Yeah, and ice expands. Expanding ice inside a high-pressure titanium manifold will rupture it instantly. So propylene glycol basically depresses the freezing point of the fluid, acting as antifreeze.
Okay, that makes perfect sense. What's the second liability?
Corrosion. The cold plates bolted to those expensive GPUs are often made of copper, aluminum, or nickel alloys. Warm, pure water moving rapidly over metal will eventually cause oxidation or galvanic corrosion.
Over time, yeah.
Right, over months and years, the metal degrades and particulates flake off. Propylene glycol solutions are formulated with highly specific chemical inhibitors that basically coat the inside of those metals, preventing corrosion and prolonging the life of the hardware.
Yeah, you definitely don't want microscopic rust clogging up a $50,000 NVIDIA chip.
Exact.
And the third liability.
Biology. Water is the foundation of life.
Uh-oh.
Yeah, if you have a closed loop of warm, pure water, it is only a matter of time before you grow a colony of bacteria or algae.
Inside the server pipes.
Yes. A biological bloom will clog that incredibly fine 50 micrometer filter, which, for context, is thinner than a human hair in a matter of hours. Propylene glycol has biocidal properties. It keeps the closed loop completely sterile.
Okay, which explains why the secondary loop is so heavily guarded and specialized. And speaking of guarding this system, the text highlights that the secondary side utilizes 2N redundant pumps.
Right, redundancy is key here. In critical infrastructure, N stands for the minimum number of components needed to fulfill the baseline requirement.
Okay.
So if a system requires 1 pump to move the fluid, N equals 1. 2N means you have double the required hardware physically plumbed in and ready to go.
So if the primary pump on the VIP loop blows a seal or just burns out its motor, the flow doesn't stop.
The pressure sensors detect the drop in flow within milliseconds. The backup pump, sitting right next to it in parallel, spins up instantly to take over the load. Because, as we established earlier, if the flow stops in that secondary loop, the silicon cooks.
Right. So managing these 2 entirely separate, highly pressurized fluid loops, rushing it up to 1,200 liters per minute, and doing it while managing microsecond pump failures, temperatures, and pressures, that requires an incredibly sophisticated brain.
You absolutely cannot manage this manually.
No, you can't just flip a mechanical switch on the wall and walk away.
Yeah.
A human cannot react fast enough to prevent a catastrophe here.
Which necessitates a completely separate, highly intelligent management layer. You are moving from heavy industrial plumbing into advanced software orchestration.
Enter the brains of the operation. Supermicro's SuperCloud Composer, which the datasheet refers to as SCC, and more specifically, its Liquid Cooling Console Module, or ACCM.
It's quite a mouthful, but it's powerful.
Yeah. The documentation emphasizes that this software manages multi-generation Supermicro servers alongside third-party systems from a single unified console.
The term you'll hear facility managers use for this is a single pane of glass. It is basically the holy grail of data center operations.
And if you look at the UI screenshots provided in the source material, you can see exactly how they achieve this. There is a module on the screen called POD View.
Right, the POD view.
It features this hierarchical nested tree view on the left navigation pane. It starts really broad. You have a data center zone called POD01. Under that, there's a subset called Group 1. Nested under that, it lists the specific IP address for an individual in-row CDU.
Getting more granular.
Exactly. And beneath that CDU, it lists the actual server racks it is cooling. AR Rack 1, AR Rack 2, AR Rack 3.
The psychological shift here for a system administrator is profound. Historically, sysadmins monitored, CPU utilization, network traffic, and storage capacity. Now they are monitoring fluid dynamics.
That's a huge pivot.
It is. What SEC does beautifully is map the physical plumbing directly to the digital workloads.
Yeah, the UI even shows a literal front-rear graphical view of the in-row CDU, sitting directly adjacent to 3 graphics of fully populated server racks. The visual mapping is just immediate.
You see exactly what you're controlling.
And the text makes a point that I think is crucial. Here's where it gets really interesting. This rack management solution allows you to align workloads with specific rack deployments, whether at the edge or even in data centers located miles away.
That geographical flexibility is vital. Let's say you are managing a global AI deployment. You are sitting in an office in Chicago, but you have a cluster of racks in Frankfurt, Germany.
Okay, miles and oceans away.
Right. And you are about to initiate a massive 2-week training run for a new large language model, and you want to push that compute workload to Frankfurt. Before you send the command, you look at your single pane of glass. You don't just check if the Frankfurt servers have enough compute capacity.
You check the cooling capacity.
Yes. You check the SEC API to see if the CDU attached to those specific racks in Frankfurt has the pump capacity, the thermal headroom, and the primary facility water flow to absorb the massive heat wave your workload is about to generate.
Wow, so you aren't just reacting to heat, you are orchestrating it ahead of time.
Exactly. It's comprehensive lifecycle management.
I have to admit some skepticism here, though, honestly.
Oh.
Yeah, I look at this beautifully unified single pane of glass UI, managing temperatures across continents, and all I see is a terrifying single point of failure. If the SuperCloud Composer server goes offline or there's a network outage between Chicago and Frankfurt, do you just lose visibility and control over a 1,200-kilogram box of pressurized liquid sitting next to your most expensive hardware?
It's the right question to ask, and it's why industrial control systems are layered. SuperCloud Composer is the orchestration layer. It's the conductor of the orchestra. But the In-Row CDU itself has its own localized hardware-level controllers.
Like its own little brain.
Exactly. The baseboard management controller, or BMC, and programmable logic controllers. If the network link to SEC is severed, the CDU doesn't just freeze up. The localized brain knows its parameters. Keep the fluid moving at this pressure. Keep the temperature at this threshold. It will autonomously manage its own survival until the orchestration layer comes back online.
Okay, so the software gives you visibility and coordination, but the hardware protects itself.
Exactly.
And speaking of visibility, the granularity of what SEC monitors is frankly obsessive. The telemetry and analytics list includes temperature, pressure, flow rate, water quality, leak detection, and power consumption.
It's functioning like a critical care monitor in an intensive care unit, but for fluid dynamics.
It really is. But the control aspects are just as specific. The software dynamically manages pump speed, primary side valves, and condensation.
Yes. Condensation.
Okay, I got to stop and ask for clarity here. Condensation. Why is condensation explicitly mentioned as a critical control factor in a high-tech data center? I thought we established this was a completely sealed, closed-loop liquid system. Where on earth is the condensation coming from?
It's a brilliant inclusion in the feature set, and to understand why it's critical, we have to revisit the thermodynamics of the primary loop we discussed earlier. Remember that the facility water, the raw street water coming into the building, can enter the heat exchanger at temperatures as low as 2 degrees Celsius.
Right, which is just barely above freezing.
Now, picture a large, uninsulated metal pipe carrying a massive volume of 2-degree water, and it is routed straight into a server room where the ambient air temperature might be 35 degrees Celsius, which is about 95 degrees Fahrenheit.
I see where this is going. If you take a glass of ice water outside on a humid summer day, the outside of the glass instantly starts sweating.
Precisely. The warm air immediately surrounding that cold pipe reaches its dew point, and the moisture suspended in the data center air rapidly condenses into physical water droplets on the exterior of the pipe.
And in a data center, having water magically appear out of thin air, accumulate on overhead pipes, and drip down onto electrified, multi-million-dollar AI servers. So that is an absolute catastrophe.
Indoor rain in a server room is a career-ending event for a facility manager.
I can imagine. So how does the software stop physics from happening?
By constantly recalculating the dew point, the CDU monitors the ambient room temperature and the relative humidity in real time. It uses that data to calculate the exact temperature at which condensation will form on metal surfaces.
Okay.
It then dynamically throttles the primary side control valves to ensure that the approach temperature, the physical temperature of the metal pipes and the heat exchanger, never drops below that specific dew point.
Wait, so it purposefully restricts the flow of the ice-cold water to warm the pipes up just enough to prevent them from sweating.
Yes, while still providing enough thermal transfer to cool the servers.
That is a staggering balancing act. It is riding a knife's edge between allowing the servers to overheat and creating a localized rainstorm inside the facility.
It's incredible math happening every second.
And if you look at the UI screenshots provided in the source material, you can actually see the software managing this high-wire act in real time.
The visual representation of this telemetry is where the abstract physics become tangible for the operator.
Let's spend some time looking at the analytics screen they provided because there is a lot of data packed into one visual here. There is a chart tracking temperatures over a 24-hour period, and it shows these intersecting color-coded lines.
Right, the supply and return lines.
Yeah, you have the coolant supply temperature, which is the VIP glycol fluid heading out to cool the servers. Below that, you have the facility water return temperature, the street water carrying the heat away. You can visually track how a sudden spike in the facility water temperature forces an immediate automated reaction in the coolant supply line to compensate.
It is a real-time display of cause and effect. You are watching thermodynamics react to digital workloads.
And below those temperature graphs, there is a whole section dedicated to CDU status over time. Most of the timeline is a reassuring solid green bar labeled good. But what I appreciate about this UI is that it explicitly includes and clearly flags red error states.
It doesn't hide the faults.
No. In fact, if we refer back to the CDU list screenshot, the system shows CDU2, CDU5, and CDU8 actively throwing an error under the control unit column. It's not just a theoretical marketing dashboard showing perfect conditions. The software is designed to scream at you when the physical hardware is struggling.
And perhaps the most critical timeline on that entire analytics page is the dedicated row for leak detection.
Oh man, just reading the states for that timeline gives me anxiety. It shows 3 possible statuses: good in green, leak detected in pink, and broken in red.
Nobody wants to see broken.
No. Seeing the word broken as an official color-coded state in a massive liquid plumbing system right next to your AI hardware is terrifying.
It is terrifying, but knowing exactly when and where a leak is detected, down to the specific CDU and the exact minute it occurred, is what allows a modern data center to survive. If the system detects a micro leak, the software can execute automated containment protocols.
So it reacts before human even knows it's happening.
Exactly. It can slam shut the expansion valves, isolate the compromised loop, and kill the pumps before a slow drip becomes a catastrophic flood.
And speaking of pumps, the UI also specifically tracks the VFD status. Now, VFD stands for Variable Frequency Drive, correct? This controls how the pumps operate.
Correct. A variable frequency drive is an electronic controller that adjusts the frequency of the electrical power supplied to the electric motor of the pump.
Instead of the pump just having 2 states like off or 100% on.
Right. The VFD allows it to spin up gradually and maintain highly specific RPMs based on the exact flow rate required.
Why is that gradual spin up so critical, though? Why not just snap the pumps on when things get hot?
Because of the massive kinetic energy we discussed earlier. Remember, you have 1,200 liters of water rushing through 4-inch pipes every minute.
Right.
If you instantly snap a massive industrial pump on at 100% capacity, or worse, if a valve snaps shut while the fluid is moving at full speed, you create what engineers call a water hammer effect.
Oh, I've heard that in old houses where the pipes bang inside the walls when you turn off the faucet too fast.
Exactly. It is a violent shock wave of pressure traveling through the incompressible fluid. In your house, it makes a banging noise. In a data center, A water hammer inside a 4-inch primary pipe can generate enough concussive force to blow out the heavy-duty ANSI flanges or shatter the titanium plates inside the heat exchanger.
Which would instantly cause that broken leak status we were just talking about.
Precisely. The VFD ensures a smooth, mathematically controlled ramp-up of fluid velocity, which the SCC software actively monitors to prevent concussive damage.
The software also tracks EV1 through EV4 status, which are the expansion valves managing the pressure as the fluid heats up and physically expands. Every single moving part, every valve, every drop of pressure is logged, graphed, and controlled.
It's total oversight.
But all of this granular telemetry, this obsessive leak prevention and dew point throttling, isn't just about protecting the local servers. The source material makes it clear that this is about a much larger global goal.
Right. If we connect this to the bigger picture, we move beyond just hardware survival and step directly into the realm of global sustainability and power grid economics.
Yeah, the datasheet explicitly states that implementing these cold plate rack-scale liquid solutions enhances PUE operational efficiency, minimizes energy consumption, and cuts down carbon emissions from fossil fuel-based power.
PUE is the magic acronym here.
Now, I know PUE is essentially the golden metric of the data center industry, but we really need to break down exactly how this math works for you. How does water cooling fundamentally alter a data center's carbon footprint?
Let's define PUE properly first. It stands for Power Usage Effectiveness. It is a ratio used to determine how energy efficient a data center is. The formula is simple. You take the total amount of power entering the entire data center facility, the lights, the security systems, the cooling, and the servers, and you divide that total by the amount of power actually being consumed by the IT equipment alone.
So an ideal mathematically perfect PUE would be 1.0, meaning every single watt of power pulled off the local utility grid is going directly into computation, and exactly 0 watts are being wasted on facility overhead.
A PUE of 1.0 is the impossible ideal. Historically, older, air-cooled data centers operated with a PUE of 2.0 or sometimes even higher.
Let's put actual numbers to that so we understand the scale of the waste.
Sure. If a legacy data center has a PUE of 2.0, it means that for every 1 megawatt of power they use to actually run the servers and process data, they have to pull an additional 1 megawatt of power off the grid just to run the massive air conditioning compressors and the huge fans required to blow that cold air around the room.
Wait, so half of the massive power bill is essentially just fighting the heat?
Yes. Half their energy goes to cooling. It is incredibly inefficient.
So how does liquid cooling change the math in that denominator?
By utilizing the physical properties of water as a transport mechanism instead of air, you drastically reduce the facility power required. We noted earlier that this supermicro CDU only requires 18.5 kilowatts of electrical power to transport an entire megawatt of heat out of the system.
Ah, right.
Trying to move a megawatt of heat with traditional CRC-RC air conditioning units would require hundreds of kilowatts of fan and compressor power. By switching to liquid, you slash the facility overhead. You push the PUE down dramatically, moving it toward 1.1 or 1.2.
You are literally shaving massive amounts of wasted power off the top of the facility's requirements. And when data centers consume power on the scale of small cities, a drop in PUE from 1.8 down to 1.2 translates directly to massive reductions in carbon emissions, especially if that local grid is powered by fossil fuels.
It makes the entire operation exponentially greener, absolutely, but it also makes it significantly more cost-effective. The single highest ongoing operational expense for any data center is not the hardware itself, it is the electricity bill.
Right.
Lowering the PUE fundamentally changes the profit margins of the facility.
Which naturally leads us to the business model of this entire operation. We've talked about the incredible physical engineering, but how does Supermicro actually deploy this software to enterprises?
The licensing model is very telling.
It is. The datasheet details a very specific tiered licensing model for SuperCloud Composer.
This is where we see the monetization strategy. The hardware provides the capability, but the software dictates the value.
The document outlines 3 specific tiers. First, there's a trial license. It offers a free 90-day trial that supports up to 200 monitored systems listed under the part number SFT SDDC trial.
Right.
Then you have the monitor license, designed for single system monitor activation, which is part number SFT SDDC single. And finally, the DCMS license, part number SFT DCMS single, which the text notes is explicitly required to unlock Advanced Baseboard Management Controller, or BMC, features.
Let's extract the business insight from those part numbers for a second. What stands out to you about that specific trial structure?
Honestly, The scale of the trial is fascinating. They aren't saying, here's a 14-day trial for a single server. They're offering a 90-day trial for up to 200 monitored systems.
Which is huge.
Yeah. In the context of dense liquid cooling, 200 systems represent a substantial deployment. That's multiple racks of extremely expensive hardware. They are essentially saying, install our software, let us physically map a huge chunk of your facility, watch the incredible granular analytics for 3 months, and prove to yourself that our telemetry manages your heat better than whatever legacy tools you are currently using.
It is an incredibly aggressive, highly confident go-to-market strategy based on the classic razor and blade model. They know that in enterprise IT, the switching costs for infrastructure management software are astronomical, not just in dollars, but in organizational friction.
Oh, absolutely. Once a facility manager gets a taste of that unified single pane of glass, and they get used to seeing the dew point throttling and the leak detection timelines all in one place, the sheer thought of ripping that software out and going back to disparate, clunky monitoring tools becomes unthinkable.
The software becomes the sticky part of the ecosystem.
And you mentioned the DCMS license unlocking advanced BMC features earlier.
Right, the baseboard management controller.
Yeah, which is a specialized service processor built directly into the motherboard of modern servers.
It has its own memory, its own network connection, and it allows an administrator to monitor hardware sensors or remotely reboot the server, even if the main operating system has completely crashed.
Okay, so by gating the advanced integration of these hardware-level controls behind the premium DCMS license, Supermicro is basically ensuring that organizations looking for true, automated, self-healing infrastructure have to fully buy into their software ecosystem.
It's brilliant product packaging.
Right.
And there is one final detail in the document that highlights this packaging perfectly, I think.
Yes, I know exactly what you're going to say. The datasheet includes literal QR codes printed right into the text.
Yes.
There's a QR code that links directly to the SEC white paper, and another one that takes you directly to the SEC webpage to apply for that 90-day trial license.
It is a remarkable juxtaposition of two entirely different eras of technology.
Exactly. On one half of the page, we're meticulously detailing 4-inch ANSI steel flanges, megapascals of pressure, 1,200 kilograms of mass, and the brutal realities of industrial fluid dynamics.
Heavy, dangerous stuff.
And on the exact same page, the call to action is basically, scan this QR code with your iPhone to start your free software trial. It bridges the gap between heavy, potentially dangerous industrial machinery and frictionless modern software as a service onboarding.
It essentially turns high-pressure plumbing into a SaaS app.
It is the consumerization of enterprise infrastructure. They have taken the daunting complexity of thermodynamics and packaged it into a user interface that feels as approachable as downloading a new app on your phone.
It really is a masterclass in making the incredibly complex feel manageable.
So let's step back and summarize the journey we've just taken through these blueprints, because we've covered an immense amount of ground today.
We certainly have.
We started by acknowledging the sheer physical reality of the AI revolution, the fact that the cloud is heavy and it is scorching hot. We explored the massive 1,200 kilogram In-Row CDU appliances sitting directly on reinforced floors, moving a megawatt of heat on just 18.5 kilowatts of power.
An incredible ratio.
We dissected the brilliant high-wire act of the two distinct plumbing loops, the chaotic high-pressure street water, and the tightly controlled, hyper-filtered VIP propylene glycol loop interfacing across micrometer-thin metal plates.
The plate heat exchanger, yeah.
And finally, we saw how the sleek SuperCloud Composer software orchestrates it all, managing dew points, preventing water hammers, and hunting for microleaks, all while driving down the facility's PUE to make the future of AI physically and environmentally sustainable.
It's a complete ecosystem.
So what does this all mean for you and for the future of the internet?
Ultimately, it means we are witnessing a fundamental, irreversible shift in data center architecture. Moving the primary cooling mechanism from the room level to the rack level is a generational paradigm shift.
There's no going back.
None. It is the industry's collective realization that if we want to compute harder, if we want to build larger and more complex AI models, we can no longer treat cooling as a facility afterthought. The plumbing has to be managed with the exact same millisecond precision as the digital workloads themselves.
Right.
This technology prolongs the life of the silicon, it ensures uptime stability, and it creates a roadmap for the AI boom to continue without hitting a thermal wall.
It is a phenomenal engineering achievement. And I want to leave you, our listener, with a final provocative thought to mull over. building on the sheer scale of the thermodynamics we've discussed today.
Oh, this is interesting.
As our global demand for artificial intelligence and big data continues to skyrocket exponentially, we are rapidly approaching a unique threshold. The limiting factor of human technological progress isn't going to be how fast a foundry can print microscopic transistors onto silicon.
No.
And it isn't going to be how cleverly a software engineer can write algorithms. The ultimate bottleneck to human advancement is going to be thermodynamics. Exactly. If tomorrow's massive data centers require vast rivers of glycol and millions of gallons of continuous primary facility water just to keep the chips from melting, it changes the map of the technological world. Will the hyperscale tech hubs of the future be built not where the electrical grids are the strongest or where the fiber optic cables are the thickest, but where the physical fluid dynamics are most easily managed?
That's a profound thought.
Are we looking at a literal return to the dawn of the Industrial Revolution, where our most advanced, hyper-modern AI cities will have to be built on the banks of cold, rushing rivers just to survive the heat of their own intelligence?
It really makes you wonder.
It's something to think about the next time you type a prompt into an AI and get a brilliant answer back in a fraction of a second. There is a very heavy, very wet, highly pressurized machine working incredibly hard to keep that illusion of magic alive. Thank you for joining us on this deep dive.